All right, we are talking about something called the central limit theorem, okay? There's a lot of words here. It says, draw a simple random sample of size n from any population whatsoever with a mean, mu, and a finite standard deviation. When n is large, the sampling distribution of the sample x bar is close to a normal distribution with that same mean and sigma divided by the square root of n, with mean, mu, and standard deviation, sigma over the square root of n. So what is this saying? Well, first, if it's already a normal population, it will be a normal sampling distribution regardless of sample size, okay? But if you have an abnormal population like this, then if I take samples of size 1, it'll look like the population. If I take samples of size 5, it'll start to centralize. See, the bump from way over here is shifting. And then if I take samples of size 10, it'll centralize even more. Okay, it's still a little bit skewed to the right? The tail on the left is way steeper than the tail on the right. But when you get up to a sample of size 25, it's very, very central, unimodal, symmetric. So the central limit theorem says, even if you have an abnormal population, if you take a large enough sample, the sampling distribution of all of the sample means will be relatively normal. Okay, so let's see it in action real quick. All right, so right here, let's take something that's like really, really crazy bimodal like that. Okay, so there's my population. Notice it has a mean of 26.4, standard deviation 15. It's clearly not symmetric because the mean is below the median. If I take samples of size 2, boop. Sometimes you get low numbers. Sometimes you get high numbers. I'm getting lots of low numbers here. Let's do 5 times. Okay. Oh, sometimes you get things from both sides. Okay. There's one towards the middle where I got one from above, one from below. Okay. But if I get them from both above, you get piles here. What you're going to start seeing is 3 piles. There's a pile over here when I get 2 from the right. There's a pile right in the middle where I get 1 from the left, 1 from the right. There's a pile over here where I get 2 from the left. And I guess there's like other piles when I get them from throughout, right? If I made this shorter in the middle, okay, then you would see a distinct 3 piles, right? Because I'm never really getting them from the middle, but I'm getting from here, or 1 from each, okay? So you see 3 piles. But notice, as I increase the sample size, now there's 4 piles. That's kind of nice. Well, let's keep going. There's 1, 2, 3, 4, 5 piles. I kind of like that. What happens if we get up to 10? Well, there's still like 11 piles, but they're becoming almost indistinguishable. See, this sample had a bunch from the right, so we got a sample. The last sample that was taken out of those 1,000 is way over here to the right. What about 15? Because you might ask, many samples. How many samples is enough samples? That's a good question, okay? Here, this sample, size 15, starting to look pretty unimodal and symmetric. Notice the mean is 25.7. Here, this mean is overshooting it a little. Maybe if we do a few more, it might get a little bit closer to 25.7, but it's still not perfect, okay? Let's try 25, okay? It's like hovering right around this 25.7239, okay? And look how nice, unimodal, symmetric. This is like almost perfectly normal, okay? Some textbooks use 25 as the number that will take the most abnormal population and make it relatively normal. If you have something with slight skew, it might only take a sample size of 8 to make it normal. So if I take something like this, that's kind of skewed, okay? Sample of 1 is going to look just like the population, okay? The more I do it, the more it looks identical to the population because all I'm doing is taking samples of size 1. Size 5, let's see. It's relatively normal, okay? We're getting there. Let's try, I said 8 might be enough. Boom. Still a little skewed right, so maybe not in this case. Let's try 12. Oh, that looks pretty good. Okay, we're still a little bit above with my mean. If I do it a few times, you'll see it hovers back close. Notice the mean and the median are almost the same, so it's not a strong skewness. Okay, clearly, if we get up to 25, that seems to be enough to normalize it, right? The mean and the median are almost identical. Okay, and so any shape distribution, as you increase the sample size, it makes it skinnier. Look at that, and makes it more and more normal. The larger the sample size, the more normalized your sampling distribution gets. Notice I'm never changing the population distribution. A sample might come from all over the place, but the mean of that sample becomes a data point down here in my sampling distribution. Many, in this case, 12,000 samples has created this beautifully unimodal, symmetric sampling distribution, okay? And so let's do a practice problem. All right, so you see that as sample size increases, you get more and more normalish, okay? So we take my essays, okay? So I write a 500-word essay, and the number of grammar mistakes that I make is not normal, but it has a mean of 2.6, standard deviation of 1.5. If you looked at a sample of 25 of my essays, then what's the probability that the mean number of errors is below 2.3, okay? So the population probably, ooh, that was ugly, looks like this, right? If the mean is at 2.6, I'm probably mostly making, it's actually probably not even like this. It's a bar graph, right? Where most of the time I'm getting 2 errors. Sometimes I'm getting 1 error. Sometimes I'm getting 0 errors. And then sometimes I'm getting 3 errors, or 4, 5, 6, 7, 8, right? And it just dwindles off. But 2.6 is my mean. Standard deviation is 1.5, all right? If I looked at a sample of 25, then now my new mu, my mu of my many x bars is going to still be 2.6 because it equals the original mu. My sigma of my x bars is 1.5 divided by the square root of my sample size. And we get 1.5 over 5 is 0.3. And you could make the argument that because there are 25, a sample size is 25, that the central limit theorem would suggest that the shape of this sampling distribution would be relatively normal, okay? And so I can say, all right, what's the probability that I'm below 2.3? I could say, oh, well, 2.3 is exactly 1 standard deviation below. And if it's normal, we can use my 2.6. Here's 2.3. And we know that this is 68, which puts 34% below. And so this would be 16%, 16th percentile. Okay. What's the probability? 16%. All right. So good luck and farewell.